We will discuss in this slide the class of problems: tractable, intractable, PNP and P complete. What is a problem? A problem is a question to be answered. What is the value of x and x divided by y? A problem usually has parameters x and y. A decision problem is a version of problem with only two possible answers, yes or no. Given two numbers, x and y, does y evenly divide as x? This is a decision problem. It will give yes or no answer. The instance of any problem will be if we are providing values to the parameters, then it becomes the instance of that problem. Now, what are tractable, intractable problems? Tractable problems solvable in polynomial time, and intractable, a problem that is not solvable by polynomial time algorithms. The examples we have already discussed. For tractable, it's like simple problem, searching, sorting, minimum spanning tree, and for intractable it is store of n. Then decision problems. So theory developed in terms of yes or no problems. So common examples for decision problems are like independent set. So the question is like, given a graph G and an integer k, does G have an independent set of size at least k? The another common problem is vertex cover problem. Given a graph G and an integer k, does the graph have a vertex cover of size at most k? Now certificate kind of problems or the examples. Now if we are asking for independent set of size k, what is the certificate that we reach the answer or we know the answer? The independent set we can show. For satisfiable formula, we can show the assignment of truth values so that we are getting the satisfied solution, that is answer true. Hamiltonian circuit problem, we can show a cycle including all of the vertices. For k coloring a graph, we can assign proper colors to the vertices so that it can be proved or certified that this graph is possible to color with k colors. Now we are considering the universe of problem, which is shown here with the Venn diagram. So here it is the total set. This circle is representing a problem area. Out of this, as you can see, there are p problems, and all other problems apart from p are under NP category. In this NP category, some problems are known to be the or called to be the NP complete problems. So in next slides we will be discussing about what do you mean by P, NP and NP complete problems. So P problems, which are the polynomial time problems. So P class problems that can be solved in polynomial time, which corresponds to problems that can be solved efficiently in practice. Right class to work with. Theoretically you can get answer theoretically, hence practically also it is easy to solve. What is NP problems? Problem solvable in non-deterministic polynomial time. So it is a non-polynomial time. It is the problem solvable in non-deterministic polynomial time by NTDM generally. problems where yes instance have polynomial time checkable certificate. So here, since it is solvable by a non-deterministic machine, that means there are multiple paths available from one state with a single input to multiple states, and out of these multiple paths only single path is reaching to the solution, and if you guess that particular path and if you reach to the solution, then you can claim that I have got the solution for a given problem. Now if you are guessed and you are claiming you got the answer, then if that solution can be verifiable in polynomial time, then we call such problems as NP problems. So problems where yes instances have polynomial time checkable certificates. Now to understand NP complete class problem, we need to consider that we need to understand first the reduction concept. What do you mean by reduction? So to understand again the reduction, I'll first discuss the problem with example. So the simple example is finding the median reduces to sorting. So what exactly this means? This means we can solve the problem median if we have the solution for the sorting, or in other words we can say that the sorting is supporting to solve the problem of median. Now what could be the steps to solve this problem? If you are interested in finding median of n items, you will very first sort the items and you will return item in the middle. So you can say that you have reduced the median problem to sorting problem. Now see the definition. Problem X reduces to problem Y if you can use an algorithm that solves Y to help solve X. So here X is nothing but you are finding median. What is your Y? Your Y is sorting. So now sorting is helping you to solve the problem to find the median. Now what is the cost of reduction? So the cost of reduction here for this example is 1, because you have to just get the middle element. So total cost of solving X will be the cost of solving Y plus the cost of reduction. So when we have such problems, then we say that X is no harder than Y. That means you are able to reduce X to Y. The another example is element distinctness reduces to sorting. So again you will take help of Y, which is sorting, and then you will check adjacent pairs. Now see here the cost of reduction. So it is now n. Okay, so now the element distinctness problem reduces to sorting, which take time of reduction as n. Now example 3, TSP reduces to sorting. So without restriction, could you solve TSP in this step using brute force? It requires exponential time, violates the spirit of reduction, so that's why we need to adjust our definition of reductions. So definition didn't say anything about how costly the reduction can be, but we want to restrict this reduction time to polynomial time. So polynomial time reduction will be the reduction where you require polynomial time to reduce from one problem to another problem. Now this is a simple example tree which is showing the linear time reduction. Just now we have discussed all finding median or element distinctness are reducible to sorting, and if you will keenly observe, the time complexity is linear, that is 1, and it doesn't have any root like n square and cube. So these are all linear time reduction algorithms. Now what do you mean by polynomial time reduction? So why is polynomial time reducible to x? If solve problem y with a polynomial number of computation steps and a polynomial number of calls to a black box that solves x. So it is notified, or its notation is y is polynomially reducible to x. So in this way we show the polynomial time reduction of y to x. Suppose y is polynomially reducible to x, and if x can be solved in polynomial time, then y can be solved in polynomial time. So the common example is the set problem, satisfiability problem, which is the hardest problem in NP. So anything in NP is polynomially reducible to set and then to 3 set. That means here set is acting as the sorting. So all NP problems, if reducible to set, then set is the hardest problem. So what we want to prove now, that all the NP problems are reducible to set, and set is reducible to 3 set. That means if we want to solve any problem in NP, then all problems need to be reduced to 3 set problem. Now we will define the NP completeness. So what are the NP complete problems? A problem exists is NP complete if very first condition x is in NP, and second, for every y in NP, just now we have shown, that is every y, all these points are considered as y, every y in NP are reducible to x in a polynomial time. So x is hardest problem in NP. So as per our diagram, set, 3 set are considered to be the hardest problem. That is 3 set again. If x is NP complete, this is another way to prove NP completeness. So if you have already some problem which is known to be NP complete, So if X is NP complete and Z is an NP and X is polynomially reducible to Z, then we call Z is NP complete. So in the example, all problems are reducible to Z and set is reducible to 3 set. So now 3 set also becomes NP complete problem. So what is Cook's theorem? The circuit satisfiability problem is NP complete. So this is a book, you can refer for this. This is a history. So populating NP completeness universe. So this is the list showing that circuit set problem is polynomially reducible to 3 set. 3 set is polynomially reducible to independent set. So this is a total list which is defining different NP complete problems. So what do you mean by circuit satisfiability problem? So circuit satisfiability is if you have been given one Boolean circuit, determine if there is an assignment of Boolean values to the input to make the output true. So for example, this is one circuit which is having combination or usage of many AND or NOT gates which are connected in some manner, and finally there are here 5 inputs. So you have to supply the value of this x1, x2, x3, x4, x5 in such a way that your final output should be true. So you have to find out such assignments to this value, and if you can assign such value, single value, even a single value which will give you true answer, then you will say that it is a satisfiable